Hello, everyone. The first speaker of the conference is Nuria Fagella from the University of Barcelona. Nuria is going to talk on virtual centers in the parameter space of meromorphic func maps.
Thank you, Vaso. Good morning, everybody here and everybody online too. And well, it's an immense pleasure to be here again after all these years or year and a half kind of that we've been all watching ourselves through a screen. So it's really nice to see you in person. And well, I hope that we have a week where we can enjoy the goods of this interaction. So thank you to the organizers for making it possible. This is we retake presential conferences with new challenges, as you can see. But anyway, I'm sure that we'll get used to it, and it's nice to have people that from home they can enjoy also the conference. So what I want to talk about today is joint work with Mathieu Astorg and Anna Benini. In fact, this is the first one of two talks. The next one will be by Anna today, and she will cover the second part of what I want to explain today. So this is about parameter space of meromorphic maps, right? So the first talk will be very transcendental in the sense of versus rational. And well, and I hope that I can explain what we've been working in these pandemic times on this issue that it's been very exciting. Okay, now. Okay, the mouse is visible from internet, yes? Okay, so as I was saying, excuse for the technical difficulties, these maps, as we all know, have a set of points for which in which they fail to be covering, which are the singular values, and I will and these points can be of two types, right? The critical values, which we are all used from rational maps, so that maps in which the map behaves like a power of z to the k for a finite number, or asymptotic values, which means that morally some preimages of this point are at infinity, not only multiple, but concentrated infinitely many at infinity. So observe that if the function is entire, what is happening here is that infinity, it is always one of these points. It is omitted, and therefore one of these asymptotic values. So this is what makes entire maps special. In reality, they are like exactly like polynomials and rational maps. So they are this very special case of this larger class in which infinity is an omitted value, exactly as for polynomials. In the moment that you let this condition go, this gives you the class of meromorphic maps in which infinity is a normal point on the range, which may or may not be critical. So for example, if you think of the tangent map, right? For the tangent map, infinity is never an asymptotic value of the function. So the two asymptotic values are plus minus lambda I, and there are no critical points. The tangent is also special in the sense that these two asymptotic values are symmetric. They behave symmetrically because of the symmetries of the map. So another example here is this family that I wrote, e to the z 1 plus lambda e to the z. So in this case, infinity is an asymptotic value only for one exact value of lambda, which in this case it's 0, right? Because the two asymptotic values, one is always at 0 and the other is at 1 over lambda. So in one value of the parameter, it will be entire. Okay, we will only restrict to the case of finite type maps in the sense that they have a finite number of singular values, so transcendental, but with just a finite number of critical and asymptotic values, like the family of the exponential, the tangent, or so many others that you can think of. And the reason why we are sticking to finite type, well, at least one of the reasons is to ensure that in the neighborhood of an asymptotic value, we can always consider the composition that you are seeing here, so that all the asymptotic values are logarithmic. And what this means is that there is always a track at infinity. Think of this as the left half plane for the exponential, on which maps infinitely to 1 as a universal cover onto, it wraps infinitely many times over the neighborhood of the asymptotic value. Okay, such a map then can be decomposed by mapping it conformally to the upper half plane, and then an exponential that makes this wrapping possible. So this is the situation we have in a neighborhood of every asymptotic value in this type of maps. So if you try to think about parameter plane in general, polynomials, rational, this is not an easy problem, because the first thing you need to know is where is your parameter space, right? What is your parameter space? So in the case of transcendental families, this is especially difficult because there are many entire functions or many meromorphic maps. This is a huge space, right? So usually the approach that we've been doing during all these years, we as the community, right, is to approach this from building from bottom up, right? So we've been looking at particular slices, meaningful ones, right, dynamically defined in general, which as of now they are relatively well understood. So the two main examples in this world would be the exponential family as a paradigm of entire. So here I should mention, or I could mention many authors, especially for the slice of the exponential family. And I will definitely not mention everybody involved, but there are plenty of work starting with Baker and Ripon and Eremenko and Liubich and Lasse Rempe in his thesis, and Schleicher with Rempe also for the and Devani, Fagella, Devani, myself, and Xavi Jarque, who all of us have contributed one way or another to describe this parameter space, and many others, I'm sure. And for the tangent map, I think there is this, I want to remark this very thorough paper of Linda Keane and Janina Kotus that described all the differences that they saw with respect to entire functions, right? And that we will talk today about. So other meaningful slices with a combination of critical points and asymptotic values have also been studied. They are in the literature. They are behind this little panel that you see here, but I could mention many of them that have been analyzed and systematically approached. So for example, in the exponential family, so for those of you that are not familiar with parameter planes, let me just mention some quickly some features that make it different from the slice of the Mandelbrot set, for example, or of rational maps, right? So in the exponential family, as we said before, 0 and infinity are the two asymptotic values, and through the whole slice. And well, actually, this is wrong. Here I should have said lambda and infinity, because I'm taking this parametrization e to the z plus lambda, right? So lambda and infinity are the asymptotic values. All hyperbolic components, and hyperbolic components, I mean these parameter values for which the exponential has an attracting periodic orbit. Remember, it can only have one at most because there is only one free asymptotic value or singular value. So all these components, these yellow, blue, red, etc., are unbounded and simply connected. Okay, and so the difference with rational dynamics is that if you look at the multiplier map, so the function that for every parameter value assigns the multiplier of the attracting cycle in question, this is a universal covering. So it's actually an infinitely to one function that maps from the hyperbolic component onto the disk infinitely many times. Now, what happens with the center? So in the Mandelbrot set, we are used to see this multiplier covering, and the preimage of 0 is exactly the center of this hyperbolic component. But here, there is no preimage of 0, right? Also because there is no critical point, so there cannot be a super attracting cycle. So what happens is that there are no centers, and the center, you have to think of it as what we call the virtual center, which happens to be at infinity. So in this universal covering map, right, the moral preimage of 0 happens to be, in this case, at infinity. So when our parameter runs to infinity in these components, in these directions, right, like not along the boundary. So as my parameter goes to infinity like this, okay, the multiplier of this cycle is going to 0 at the same time that the cycle is just escaping to infinity. Okay, so when we go to the tangent map, we see something essentially very different. What we see differently is that most of the components, as you can see, are bounded, excuse me. So in this case, we have two asymptotic values that are free to tied together, and infinity is not an asymptotic value in this case. But when we look at here, this is not true, all connected components except this one of period 1 and this one of period 2, the two big ones that you see left and right, all the other hyperbolic components are bounded, right? In obvious difference with the exponential family. All these components are bounded, simply connected, but the multiplier is still a universal copy. So where is this virtual center that in the exponential family happen to be at infinity? So in this case, there are again no parameter rays, like in here we don't have any parameter rays, but what we have is a finite virtual centers. So we have finite parameter values such that as the parameter approaches this parameter value here, right, as I tend to this point on the boundary of the component, my cycle is, one of the points of the cycle is moving towards infinity, and the multiplier of the whole cycle is tending to 0. Okay, this is what we call virtual centers, and they are, in this case, finite and all over. These points for which, so this is one of the features that we see in the parameter space of the tangent map or other meromorphic families. Another special thing that happens with meromorphic families of maps, and does not happen obviously neither with entire nor with rational or polynomial, is the existence of truncated singular orbits. So not every orbit can be truncated because it bumps into a pole. In particular, the orbits of asymptotic values can be truncated. So there are parameters for which the asymptotic value simply jumps onto a prepole and therefore is mapped to infinity after a certain number of iterates. So in '97, when when Linda and Janina wrote this paper on the tangent map, they could prove for this particular family that all these virtual centers are exactly these asymptotic parameters. So these points that you see here and everywhere actually, right? So this is the component, the hyperbolic component, one of period 2, one of period 4. This point they share in the boundary is a virtual center on one hand, right? It's a parameter for which the cycle has escaped to infinity, has disappeared into infinity, but at the same time, it's also a parameter for which the singular value, the asymptotic value, has bumped, collided with a prepole. Okay? And they prove that the two things were sorry, this is lambda 0I. Yes, this is lambda 0I, excuse me. This is lambda 0I. Thank you, Luca. The proof uses very strongly the combinatorics. So the idea of the proof is very nice, but to make it work, you really need to use the combinatorics of the tangent. Okay, so you really need to use the particularities of the family of the tangent, this tightness between the two singular values, the fact that there are no critical points, etc., etc. Okay, any questions until here? So in a recent work of Linda and myself, we made an attempt to generalize some of these features. But so we generalized it where? So we considered what we called dynamically natural families, which were the most similar thing we could think to these two slices that we've been talking about. Okay, so we wanted one parameter family so that we could talk about parameter planes, and we wanted only one asymptotic value to be bifurcating at the same time. So we could have other singular values, but our intention was to basically have one-dimensional families. And we could generalize some of the results in this. What we studied were precisely these quotes, hyperbolic components, or let's say it another way, components for which there was an attracting basin containing only one asymptotic value, the one that is giving rise to the component. We call them shell components because of this form that reminds you this the fact that it's an infinite covering with the multiplier gives you these cusps at the preimages of one, no, parabolic cycles, and these parabolic cycles accumulate onto this unique. We proved that in a fair degree of generality, these virtual centers were unique in each of the components, so that every component has a point on the boundary, maybe at infinity, like it would be in an entire situation, for which the cycle is like escaping to infinity and with the multiplier going to zero. However, the main what we couldn't prove in this paper is that if you have an asymptotic parameter, so if you have a singular value for which, a parameter value for which your singular value collides with a prepole, this is actually a virtual center. Okay, so are all these points, you can find them algebraically somehow, right? Parameter values for which the asymptotic value maps to infinity eventually. Are they all located at the bifurcation locus, at the boundary of a hyperbolic component, or at least in this setting, in this one-dimensional setting? So this is, we proved things about the components, but this is, I think, the question that we were not able to solve at that moment. And this is what this first part of the talk is about. First part meaning my part, then Anna will talk about the consequences of this. But what I want to say is, what I want to show you today is how we approach this question in a much more general setting, in which it is possible actually to prove this conjecture for a very, very large set of functions. And which is this setting? This setting is the setting of natural families of finite type. And natural families, we've just taken this name from the natural parameter space that is described in Eremenko and Lyubich. So what we will be considering are families of meromorphic maps of finite type, but such that you can write them in this way. So given a base map, it would be this F lambda 0. We will consider equivalencies, not conjugacies, equivalencies. So M will be our parameter space, simply a connected complex manifold of any dimension. So as many parameters as you wish, but we will consider maps that are equivalent, QC equivalent to the base map F lambda 0. Okay, so we want them to be quasi-conformal homeomorphisms, and we want them to depend holomorphic on lambda. You should think of this, well, we also require that infinity is fixed by the left one, and this is just to ensure that infinity is always an essential singularity. And we will consider at the base point, these maps are obviously the identity. Now, you have to think about this parameter space as maps, as a family of maps for which the number of singular values stays constant and not colliding. This is basically what you ensure, okay? Because since these are homeomorphisms, if f lambda 0 has n singular values, f lambda has n singular values, and they move holomorphically with the parameter. That's basically it, but they are not conjugate, they are just equivalent, okay? So this is a huge set, but it has very, very nice properties, and it allows you to prove a lot of things by move in parameter space precisely, by translating your questions on the family f lambda via this diagram to questions on one single map of the base point. Now, at the beginning, this looks very strange, and you say, but how do you, but it turns out that that most one-dimensional families that you know are natural. For example, you can decide, of course, which family of QC homeomorphisms you take. You don't need to take all possibilities. So, for example, lambda tangent of Z would be on the left, you would always put the identity, the base map would be the tangent, and the right family would be a conformal map lambda Z. So lambda tangent Z is a natural family as the exponential, as the sine, as the trigonometric. So many that you can write, they can be expressed in this way. In fact, in this particular case, phi lambda is conformal, right? But if you want to consider it maximal, if you want to consider all QC homeomorphisms for which this works, then the nice thing about this is that you get a manifold of dimension n. You can give it a manifold structure of dimension n, and this is in fact what Eremenko and Liubich and Goldberg and Keen used in order to prove the no-wandering domains theorems for finite type. Okay, that this parameter space actually has the same dimension as the number of singular values that you are considering. Okay. So this approach is the one used, as I said, in Eremenko and Liubich. And let me say that in this setting, you can, so what I'm going to do now is, and now I told you in the setup that we will be working, and now I want to call your attention to two phenomena that are purely transcendental, right? Two of which actually even purely meromorphic, but let's say purely transcendental. So if you want to follow your periodic orbits, we all know that the implicit function theorem tells us that as long as we are not parabolic, you can be followed around, right? Until when? When does this break? So either because two of these periodic orbits that you are following collide, creating a parabolic cycle, and therefore your implicit function theorem stops working, or, and this is purely transcendental, your cycle that you were happily following, one of the points just disappears into infinity, exits the domain of the function. In a rational map, this makes no sense because the domain of the function is the whole sphere, there is nowhere to go, right? But in a transcendental map where infinity is not in the domain, so we are not in a compact space, and a cycle, while being perfectly followable, it could just exit the domain. And this could happen a priori every time that infinity is not part of your game. So cycles may disappear into infinity or exit the domain. Another thing that is purely, and this is purely meromorphic actually, is that orbits, I've said it already, but singular orbits may be truncated. So you may simply collide into a pole, and your orbit, and in particular your singular orbit, may collide with a prepole and go away, right? So let me go into these two phenomena separately. So let's think for a moment what it means that a cycle disappears to infinity. So a cycle exits the domain, this is a definition, or disappears to infinity at a certain parameter value if there is a curve of parameters converging to this parameter value such that one of the points in the cycle limits infinity. Okay, this is the intuitive definition that we would all give. And I want to show you this picture because it's very nice, but Anna will talk more. We will not need it. I just wanted to show it to you. Anna will talk more about it later. Let me just observe that this can be formalized in this very pretty way, in which if you consider the set of pairs lambda z, for which z is periodic of period n for the parameter lambda, then you could draw your dynamical plane on the vertical axis, your parameter space, your manifold on the bottom. And then this is basically what I just explained in the slide before. My periodic points of period n, or fixed points of f to the n, can be basically followed unless, so we could draw these manifolds for each of the periodic cycles that we follow, the periodic points that we follow, and then collision of two periodic orbits translates into critical points of this map, because notice that when I take lambda c in the range, I cannot take a proper inverse here. So this is a critical point, 2 to 1, or asymptotic values of this map, because when I look at a neighborhood of lambda 0, simply my periodic point has disappeared into infinity. Okay, so in this way, if you consider this projection map from the manifold Pn to the parameter, so to the first coordinate, it turns out that these two ways of breaking the analytic continuation of your orbits can be explained as either critical points or critical value or asymptotic values of critical values or asymptotic values of your projection map, okay, or accumulations of these, of course. So as an example, in the function lambda z plus z to the z, it's easy to see that if lambda goes to 1, this map has no fixed points, right? So all the fixed points that are there all the time, when lambda moves toward the particular point, lambda equals to 1, every fixed point has escaped to infinity. So Eremenko and Liubich, in fact, in their paper about entire maps of finite type, and in particular natural families of entire maps of finite type, their main theorem is to say that in entire functions, when you are in the entire world, pi1, this map I just showed you, has only algebraic singularities, which is to say that cycles in an entire function cannot disappear into infinity as you approach a finite parameter value. Okay, so this is not true only for the exponential, in which, by the way, you can prove this by hand, right? But they prove that it's true in total generality in the parameter space of entire maps. Okay, however, in meromorphic maps, we've seen that it is possible, right? So for the tangent family, we've seen parameters for which the cycle disappears into infinity. So in the meromorphic world, this is a real possibility. Okay, second ingredient. Remember, we said we will talk about cycles disappearing into infinity, and then this other algebraic thing, which is singular values with truncated orbit. This is what we call singular parameters. So we say that a parameter is singular if there is a singular value v lambda, such that when I look at v lambda 0 and I iterate n times for f lambda 0, is mapped to infinity. Okay, and also we will call it singular if this is not a persistent thing. So if in the whole slide the same thing is happening, then there is nothing singular about this parameter value, right? So a singular parameter will be a parameter value for which some asymptotic value or critical value has a truncated orbit. And we will make a difference between a critical parameter or an asymptotic parameter, depending whether the one that has a truncated orbit is critical or asymptotic. Okay. For example, if you take the tangent map and you take the value pi I over 2, which is a perfectly okay point, parameter point in the plane, notice that in this case the two asymptotic values, which are pi over 2, if you substitute them into the tangent, they both are mapped to infinity. Okay, so this would be pi I over 2 would be an asymptotic parameter. And let me say that all these elements that I've presented, these singular parameters, these cycles going to infinity, all of these has a strong relation with the global study of the bifurcation locus of these families. But this is the content of Anna's talk, okay, later. So what I will concentrate is in that conjecture I mentioned at the beginning. So let me show you one of these families, for example. I will not entertain myself too much here because obviously we are out of time, but this is an example of a two-parameter family, actually three, right? Because it has a critical point, an asymptotic value, and infinity is a third asymptotic value all the time. So it's nice because you can play with the interaction of these two, and on top, you have 0 always as a fixed point with constant multiplier 1/2. So there is always the basin of 0 that requires one of the singular values to be there. So if you draw the parameter space of this function, we see two very distinct regions. All this green area here is where both singular values are in the basin of 0. Now everything that you see in this circle is actually when the critical point exits this basin and does whatever it has to do. And you see a picture like this. All these points here at the top of these brushes are precisely as critical parameters. So parameters for which the critical value maps to infinity. And on the other hand, everything that you see outside of this part is an where the asymptotic value exits the basin and does whatever it wants to do. And here we see these components that are essentially very different. They are all shell components, infinite degree covering, and you see all these asymptotic parameters in the boundary of these components. So this is, I mean, we would need a talk to analyze this closely, but it's just I wanted to show you where these asymptotic parameters live, right? And these singular parameters. So let me just give you a last concept before we state the theorem and we try to explain how you relate these things. So the last concept I want to talk is what we call a virtual cycle of period n+1, for example. And this is just a sequence of numbers. Infinity may be part of them, right? That follow basically, it's basically a cycle, a true cycle, in which infinity is allowed to be part of it. So for the moment, it's only an abstract definition. You say that this sequence is a virtual cycle if, as long as they are, as it's cyclically ordered, as long as they are finite points of the plane, f needs to map each of them to the next. And in the moment that you find infinity, so if one of them is infinity, the rule says that the next one needs to be an asymptotic value. And the previous one needs to be a pole. Okay? So this is what Linda and Janina already called virtual cycles. Obviously, when you have an asymptotic parameter, so when you have a singular value, that an asymptotic value that is a pre-pole, this can be written as a virtual cycle. For now, this doesn't mean anything. But obviously, if you have here, for example, an asymptotic value that after 3 iterates is mapped to infinity, you can write A7, A1, A2, infinity, A7, etc. And this is a virtual cycle as the ones that we just defined. So the theorem that I will present this theorem in two parts. So in this setting of natural families that we've been talking about, so I didn't put the hypothesis, but it's exactly the setup I've described. for a given family, natural family of meromorphic maps of finite type. Those are all the hypotheses. The first thing we prove is that if there is this phenomena of a cycle disappearing to infinity, this always needs to involve a parameter that is a prepole, a singular value that is a prepole. Okay, so a cycle disappearing to infinity implies that that parameter value for which this is happening is singular. More precisely, what we prove is that you do converge, this cycle that is disappearing does converge to one of these virtual cycles, which needs to contain, therefore, an asymptotic value, or, and this is something we try to exclude in the future, but for now, or maybe a critical point that is mapping to infinity after a certain number of iterations. Okay, so this is not difficult to prove, right? The first part. So to see that actually you go to a virtual cycle is something that you can draw and see. So if you just take, suppose you have a cycle that disappears to infinity, here is your z of t mapping to infinity, then you can just map this curve by the corresponding function f lambda of t. Careful, because this is moving with a parameter. Huh? Let's call x1 of t to the image and x2 xn minus 1, and by definition, except at the limit, this is an actual cycle. So this point maps to this, and comes back by the corresponding parameter value, right? So what you can see is that these curves that you can draw here, they are all eventually mapped by the limit map to infinity, so they need to be prepoles, and therefore by discreteness of the prepoles, they actually need to have a limit. So all these curves have a limit, and if you call this limit am, it's just a point, right? Then here you can see the nice, what this diagram allows you to do. So I'm going to do this because you see that why this diagram really helps you. So suppose you have one of these curves, xm of t, one of them whose limit is infinity, right? At the next, when you map it by f lambda of t, we've said that it needs to have an image. We don't know which one. But if you lift these two curves by the corresponding quasi-conformal maps at the parameter that is the one at every point, you are then left with two curves on a one dynamical plane, the dynamical plane of f lambda 0, right? Since this one needs to preserve infinity, this is a curve of points tending to infinity, which by the commutation of this diagram by f is mapped to a curve of points mapping to am plus 1, because remember that at the limit point, this is the identity. So you've actually constructed up here, where the parameter has disappeared, an asymptotic value. So this is what tells you that this cycle needs to have the properties of the virtual cycle. But what I wanted to show you here is that the fact of having these natural families really allows you to work with this very difficult thing, which is usually to play with parameters that move all the time, right? And so many dynamical planes at the same time. Okay, what's the hard part in this theorem? The really hard part in this theorem is to prove that this does not happen persistently. So that this is really a singular thing that is going on, okay? Okay, so let me also say that it generalizes the theorem of Eremenko and Lyubich that I mentioned, that there are no cycles exiting to infinity for entire families. So I will not go into why, but it's a corollary. Okay, we want to get rid of this possibility of the critical point being there, but this is work in progress. But let me say that if you know on your particular family that there is no persistent singular value mapping to infinity, then asymptotic value, then it's always an asymptotic value, the one that is playing this role. And finally, so what is the converse of this theorem, which I think it's something, it's the one that proves the conjecture I mentioned at the beginning. So the accessibility theorem tells you that the converse is true. So if you have one of these algebraic conditions, an asymptotic value mapping after a certain number of steps to infinity, this parameter value is always, just to fix ideas, one of these points in the boundary of a quote hyperbolic component. More precisely, what I'm saying is that if I have lambda 0 an asymptotic parameter, at that parameter value, there needs to be an attracting cycle which is disappearing towards infinity. So it's an accessible point from the inside of some component for which there is an attracting cycle. Of course, we are in who knows how many dimensions. We are not saying about anything about if this attracting cycle has one or more singular values in its basin. That we say nothing. In the particular case of the one-dimensional slices that we've been seeing, it would be saying that all asymptotic parameters are at the boundary of shell components. But here, this is much more general because M is just a connected manifold, complex connected manifold, right? So what we are saying is every asymptotic parameter, so the solutions of this equation that you can write, they are all accessible through a curve of parameters for which an attracting cycle is just moving slowly towards infinity, slowly or rapidly. So this proves the conjecture I mentioned at the beginning. And let me give special credit here to Lasse. So in a talk that Mathieu gave in the Liverpool seminar, he really made a very big improvement in this statement. So what we had before talking to him was a very strong condition for this parameter, an extra hypothesis that said that in order for this to be true, our tracts, the asymptotic tracts, needed to have some nice geometry. So we were worried that if the tract was very thin at infinity with like an exponential cusp, the derivative would not work, the derivative of the conformal map would not work as we needed in order for this to function, right? It could kind of counteract the exponential contraction that you're supposed to have in a tract like that. And Lasse pointed out that even without this geometric condition, everything worked fine. So we are very grateful to him because the hyperbolic estimate that he gave us really solved the whole problem on this geometry of tracts. So, well, thanks, Lasse. And now I don't know how I'm doing time-wise. Probably terrible, right? Because okay. So let me, I think in 5 minutes would be okay. Okay, so if 5 minutes are okay, I would like to give you an idea of the proof of this theorem. So the idea is the following. So put your, remember what we are trying to prove, right? So we are trying to prove that if lambda 0 is one of these parameters for which the asymptotic value is mapped to infinity after n iterates, here we are, this is exactly what it says here, then we need to build this curve of parameters with this attracting cycle in all of them, such that the attracting cycle has to just go away as I approach lambda 0, right? So let's take f lambda 0 as our base map in this diagram. You can always do this by easily. And then the situation we have is that we have a tract at infinity. So my f is my base point. And this is my asymptotic value. So I can take a neighborhood and then I know that this tract is mapped to this neighborhood of the asymptotic value as an exponential, basically, right? So phi is a conformal map. And this f can be written as phi first and then exponential to map to the neighborhood of the asymptotic value. This is really where we use finite type, okay? To be sure that this is always the case, that we always have logarithmic asymptotic value. Okay, now it's when we turn on the parameter. So we use our quasi-conformal maps, phi lambda and psi lambda. And then this T, of course, becomes T lambda, it all moves. And this V, this neighborhood here becomes V lambda, it all moves. Our V is V lambda, which moves holomorphically, right? But still this commutes. So for every parameter value, F lambda, basically it's like going first here, observe that this is just this composition, and then doing this exponential and then mapping down, right? So there is a commuting, and this diagram commutes in all directions, okay. Now, what do we want? We want a curve of parameter values limiting at lambda 0, right? Such that when I move along this curve, I want the following. When I move along this curve, my goal, and you'll see why, is that so if I look at how my singular value moves and I map it by F lambda to the n, I want to be inside, well inside this tract, okay? And what does it mean well inside this tract? I mean with this that when I look at it in the left half plane, I want to be exactly on the negative real axis. This is like the direction in which there is most contraction. So I want a curve of parameters such that for each of these parameters, as I iterate my asymptotic value n times, which remember at the limit it's infinity. So when it's not quite at the limit, I want to see if I can match it to be exactly inside the tract and in the a very contracting direction. So that you'll have to believe that I can do that. It's not difficult to see actually that I can do that using this left side of the diagram, because really you can define the map from parameter space to the dynamical plane of F, in which basically this neighborhood of lambda 0 maps to a neighborhood of infinity. So as a branch cover. So I really can find a curve of parameters that under this map maps to exactly where you want it, and this can be brought down as you more or less organized it here. So believe me that you can actually find this curve, and if you trust me on that, then the construction begins. And the idea is easy, and it's not so different from what Linda and Janina used, except that in there they had the tool of knowing which function they had in hand, right? And here you don't. So what we are trying to do now is to build an attracting cycle for each of these T's, which means, and the way we'll do it is to take a set and show that it maps under n+1 iterates strictly inside itself, right? And which set will be that? So just take a disk here on the negative real axis. Of course, T is, you have to think that T is as close to infinity as you wish. Pull it back here. This is what we call dt. And now pull it back under F lambda to the n, right? And yes, I'm in 1 second. And what we'll show is that after one more iterate, it really comes inside itself. So what we want to show is that this dt after one iterate maps very well inside this disk that you showed here. And this is just, on the one hand, this very strong exponential contraction that you do when you go in this direction. This brings you to a very tiny place because you've used the exponential here. And on the other hand, an estimate that tells you that this big set needs to contain a definite disk that is much larger than the radius you considered before. So, well, I'll be happy to discuss this. This estimate precisely is the one that we needed on the derivative of this map, and that Lasse very generously shared with us. And this is it. Since this map UT maps n under n+1 iterates inside itself, and as t goes to infinity, this is tinier and tinier inside it, the multiplier of this cycle is actually tending to 0 as t goes to infinity. And that's it. I just want to say, advertise that Anna will be talking about the consequences of this theorem in the global stability analysis of these functions in the sense of Magnès and Sullivan. And I want to say, dziękuję za uwagę.
Are there any questions?
Yes, I've got a question about the point that you mentioned with the critical points. So you were saying you would like to exclude this possibility of a critical point creating these disappearing cycles.
Yes, so we have when we are, sorry, it's here, yeah. So yes, in this proof at this moment, we cannot rule out that that this asymptotic value we have in the virtual cycle might be persistent. If it is, then we can show that there needs to be a critical point that is actually being active and being mapped there. But our intuition says that there should always be an asymptotic value. But of course, at this moment, we cannot exclude this possibility.
So the problem occurs, the proof occurs if you have an asymptotic value, but this asymptotic value is persistent, and then you also have a critical point which is non-persistent.
Exactly. So in a family with no critical points, this is not an issue.
And I guess in particular in the if you take the full Eremenko-Ljubic family, then again that wouldn't be an issue because you wouldn't have any persistent asymptotic values in there.
Oh, that's a good question. So you say if I take a maximal natural family, right?
Yes, yes.
Probably you're right, because so this I have not thought, but I think you are right that if you really take it maximal, there is no persistence anywhere. I mean, a persistence like that would kind of reduce the family itself, right? So
yeah, you should obviously always be able to destroy it. So, but in that case, probably this is true. Thank you. Yes. Yeah. But yeah, it would be interesting to exclude this case with the critical point.
Yeah. Clearly. This is annoying, huh? Believe me, we've tried. Okay.
Any more questions or comments for Nuria? Sure.
So, sorry. So this idea of the proof that you did at the end, it reminds me a lot. The Devane is, I don't know, it was 85 or something like that. He was creating given lambda equal to 1 for the exponential, a set of lambda n's that tends to 1, where for each one of these lambda n, you have an attracting cycle of period n. And then, but then at the end, so the limit, it is the Julia set is the whole plane. So it is, but it's kind of the same because you are constructing, I don't know, he didn't do that with a curve, but he did with a set of parameters for which you have this attracting cycle, and at the end, lambda equal to 1, you have the Julia set. Then these cycles that he's creating, I think they are getting closer to 0 and infinity too. So in some sense, it is like disappear.
Well, I mean, this is obviously not a new idea, right?
No, I'm just trying to see
make it work, because if you know which function you are dealing with, right? If you can make a computation, lambda e to the z, or lambda tangent of z, it's one thing. And another thing is to be in who knows where, right? In these very general slices in which the information you have is the information you have, period. So I think the idea, of course, it's not new, and you are totally right. I mean, it's been used this is exactly what you do when you want to show things in parameter space that you are approximated by hyperbolic components or whatever, right? It's just that in general, it's delicate to make the thing work. That's it. But yes, you are totally right that this is very similar. In fact, here, if you happen to be in a one parameter family, the limit is the Julia set, and the limit is also the whole plane, of course, because at the limit your asymptotic value is compromised. It's in the Julia set, so there are no hyperbolic situations. So it's very similar. You are totally right, Xavi.
Okay, we're running a bit behind schedule, so maybe we can thank Nuria again for a great talk. And I suggest we start in 2 minutes.